Let's welcome Fatih Kaleoglu, who's going to talk to us about cloning games.
Hello, everyone. This is joint work with Prabhanjan Ananth and Chipeng Liu. So what are unclonable primitives? They are cryptographical primitives that are based on the no-cloning theorem from quantum mechanics. And based on what the functionality we deem is unclonable, we get different primitives. For instance, if being a valid ciphertext or a valid decryption key are the functionalities we're interested in, it's going to be unclonable encryption and single decryptor encryption. Or if it's evaluation of a hidden function, it's going to be called copy protection. So these three are the primitives of focus in our work. And similarly, you can think about public key quantum money and so on as unclonable primitives. So let me say a few words about the prior works in these three primitives. As for unclonable encryption, it was introduced in 2020, and currently we know how to achieve it in the quantum random oracle model using coset states, which are highly entangled states. And we've also had works that consider some variants of it. Single decryptor encryption introduced in the same year. And we know how to achieve it in the public key setting using very heavy assumptions, such as post-quantum I/O. And we also know a little bit about how it relates to unclonable encryption and copy protection. And talking about copy protection, about that, we know that in general, it's not possible to copy protect arbitrary functions in the plane model. And we also know how to do it in the random oracle model for specific functionalities. So what's a gap in these works? If you look at them, you would notice that most of them focus on feasibility of certain primitives. And there are fewer works that focus on the implications between different primitives. And we also want to understand techniques used in particular works that sometimes get applied in follow-up works. We want to understand how general their range is. So why do we care about the implications between different primitives? Firstly, we want to understand what computational assumptions are necessary to achieve each primitive. And in the classical crypto world, we've done a very good job over the years, and we have this Impagliazzo's 5 worlds with numerous black box separation results. So we have a pretty good understanding of the different possibilities and the hierarchy of different primitives. Ideally, we would have something similar for unclonable cryptography. Secondly, we would like to understand what types of states are necessary to achieve each primitive. So if we have black box constructions from one to another, we would find out that we could use different types of states. And we care about this because some of them might be more feasible in near-term quantum computing, for example. Next, there are different security definitions for each primitive that might result in qualitatively different notions. For example, I'll mention later in the talk, there's something called different challenge distribution settings, independent and identical. And we want to understand how that affects the feasibility of the notion. And finally, in the classical world, there are standard techniques such as the hybrid method that lets us understand these relationships. And a lot of these techniques seem to fail in the unclonable setting. And we want to understand, in general, which of these classical techniques are applicable. So our contributions, I will list them here. Firstly, we achieve the first information theoretically secure construction of single decryptor encryption. And next, we achieve unclonable encryption in the quantum random oracle model and copy protection for point functions in the same model using unentangled Wiesner states, whereas prior work used coset states. And we show how different challenge distributions are related for a general class of primitives, including single decryptor encryption and copy protection. We also give a new construction for encryption with certified deletion. And a few of these results also provide an arguably simplified proof. conceptually, we state our theorems in this framework called cloning games, which is meant to capture most unclonable primitives and provide a new way of thinking about how they relate to each other. So let me get into more details of cloning games. So intuitively, we want to capture any primitive that involves an unclonable quantum state, which is also known as a quantum token. And this state is useful to pass some one-round verification. However, this functionality of being able to pass that is unclonable. So syntactically, it's a security game between a referee and the cloning adversary. The cloning adversary consists of three parties, Alice, Bob, and Charlie. And there are three phases of this game. The first phase is the setup phase, in which the referee generates a token and sends it to Alice. In the splitting phase, Alice will apply a CPTP map to create a bipartite state, and one register will be held by Bob, the other will be held by Charlie. They could share entanglement, however, they're not allowed to communicate. So in the verification phase, the referee will send each of the two parties a challenge, and they're required to reply with an answer, which will be verified by the referee to be either accepted or rejected. And depending on how these challenges are correlated, we define the independent challenge case and the identical challenge case. So the security of a cloning game says the probability of both answers being accepted is not much greater than what is trivially achievable, which I'll describe in the next slide. And correctness says you can always make sure that one of the parties is accepted by sending the token to them. So the trivial cloning attack indeed is just sending the token to one party, meaning you don't bother to try to clone the state, and using just the entropy of the problem itself, you try to generate an answer based on the challenge. So this captures, as I said, many unclonable primitives. For example, unclonable encryption can be thought of as the token being an encrypted message, and the challenge being the secret key, and the answer being some bit of information about the message. Similarly, copy protection, the token will be a copy protective function, and in the verification phase, Bob and Charlie will get inputs to this function and be asked to evaluate them on these inputs. And almost all unclonable primitives can be fit into this framework, with one exception potentially being one-time primitives. So I talked about independent and identical challenge settings. So we showed that if a cloning game is evasive, meaning the trivial success probability is negligible in the security parameter, then independent challenge security implies identical challenge security. In particular, you can apply this to single decryptor encryption or copy protection within certain parameter regimes. So let me talk a bit about the techniques we use in the paper. The first major technique is starting with prior work by Anand et al., which showed unclonable encryption and copy protection for point functions in the quantum random oracle model using coset states. And that paper relied on program testing techniques. And we show how to get rid of the coset states and replace them with a general class of states which satisfy something called augmented security. And we show that Wiesner states in particular satisfy that. The second major technique is this work by Bitansky et al., which will be presented on Wednesday in this conference. And we show how to apply their theorem, which lifts classical reductions to quantum in the unclonability or the non-local setting. So talking about the first technique, we call this weak unclonable security for this quantum token a search game where both parties are asked to output a message of high min entropy. And we define augmented security of such a game where we give more power to the adversary by allowing them to access this oracle, which checks whether the query equals M or not. So for coset states, this was known, but for unentangled states, it was unknown. And why do we need this? Because in prior work, AKLLZ, in the second step, which is a reduction from identical challenge setting to independent challenge setting, the reduction crucially uses the fact that these oracles are accessible to it. So combining our result that we can generically augment any weakly unclonable secure state to augmented security, and the result from Brabant-Lord that Wiesner states satisfy this, we achieve our result. So moving on to our second technique, which is lifting classical black box reductions. So the prior work did this in the plane setting, and we do it in the non-local setting where you have two non-communicating adversaries, such as we have in our cloning game. And to summarize the prior work at a high level, what they do is they start with a quantum solver, and in 3 major steps, they make the solver a stateless one. And once your quantum solver is stateless, then if there's a classical reduction, that trivially translates to a quantum reduction. So the key step is the first step, which makes the solver persistent, meaning it can solve multiple instances of the same problem. And the main technical contribution is generalizing that step to the non-local setting. And what that step looks like is you take the solver, you run it once, and the state has changed, but you apply some state repair procedure, and you don't necessarily get the original state, but you recover a state which has similar success probability. So what we show is that you can do this locally for each of Bob and Charlie. And as long as the challenges are independent, it still works. And in order to prove this, we rely on we look at the Jordan decompositions. If you've heard of Jordan's lemma, it's the same Jordan. And by analyzing the Jordan decompositions of Bob and Charlie separately, we prove our results. And as a corollary of our non-local lifting theorem, we achieve the theorem I mentioned about independent challenge security versus identical challenge security, meaning any evasive cloning game, which is independent challenge secure, is also identical challenge secure. We also achieved the one-time single decryptor encryption construction in the plane model as a corollary of this theorem. So I'll conclude by mentioning some open problems. The first one is, can we get rid of the evasive requirement in our theorem, which relates different challenge distributions? The second problem is, can we get rid of the random oracle? Can we instantiate it in our unclonable encryption and copy protection constructions? And this would solve a long-standing open problem of achieving unclonable encryption in the plane model. And finally, can we remove the black box and non-adaptive restrictions, which are inherited from the prior work BBK? That's, I think, a very interesting research direction. And that's it. Thank you for listening.
Okay, thank you, Fatih. Questions?
Could I ask a question here? Yeah, thanks. Could you explain a bit why one-time primitives are tricky to formulate in this framework?
So it doesn't fit the syntax directly. You can still make it work, but you need to sort of look at randomly sampling challenges and play with. So for instance, one-time primitives say you can use the primitive once, and so using the primitive once, like do you incorporate it to Bob or do you incorporate it to Charlie? So there are a few decisions you have to make. At least in the syntax we presented in our paper, it doesn't directly fit, but conceptually it still fits.
Other questions? So you may have already answered this, but let me ask anyway. So your framework of games, can that be augmented to allow the adversary to have oracles that are related to the state? Like, let's say, the ability to reflect through it or to project onto it, or to perform the two-outcome measurement.
I see. We already allow the adversary to have access to random oracle, for example. So we can, in general, fit oracles. I don't think anything should go wrong if the oracle depends on the state, but I haven't thought about it directly.
I mean, I guess there should be some limits, right? I mean, if I can repeatedly verify whether I have the state or not, I can eventually clone it. So
right. I mean, it could be the
yeah.
case that you don't have any secure games in the model, but you can still define the model with that oracle. Yeah.
Okay, great.